Before sight, before flight, before the first step on land, a revolution was stirring in the ancient seas. It wasn't a cataclysm or a continental shift, but something far more intimate, a biological innovation that would forever alter the course of life on Earth. It was the birth of the jaw. This simple hinge of bone, armed with the planet's hardest natural substance, transformed passive filter feeders into active hunters and the hunted into formidable defenders. It sparked a biological arms race that has raged for over 400 million years, shaping every creature from the mighty Tyrannosaurus to the smallest shrew. This is the story of that innovation. It's the story of how the simple act of eating dictated the destiny of all life, including our own. This is the evolution of the bite, the tool that built the world we know. Imagine an Earth teeming with life, yet silent. Not a roar, not a cry, not a single crunch. This was our world 500 million years ago, during the Cambrian Period. The oceans were a vibrant, swirling soup of creation, a biological spectacle known as the Cambrian explosion. Life had burst forth in a bewildering array of forms. Trilobites, ancient relatives of insects, scuttled across the seabed. Strange, alien-like creatures drifted through the currents, and among them, our own distant ancestors took their first tentative steps on the evolutionary stage. Creatures like Pikaia, a small, leaf-shaped swimmer, were among the first to possess a notochord, the precursor to a backbone. They were chordates, the pioneers of our own lineage, but they, and almost everything else in this bustling marine metropolis, shared a profound limitation. They had no jaws, and they had no teeth. Their existence was defined by passive consumption. They were filter feeders, mud grubbers, and particle grazers. They drew nutrients from the water column, or sifted organic matter from the ocean floor. Predation, as we understand it, was a rudimentary affair. The apex hunter of the time, Anomalocaris, was a formidable creature with grasping appendages, but its mouth was a circular plate, ill-suited for tearing or crushing. It could seize soft-bodied prey, but it was not a biter. This was a world governed by suction and absorption. Life was a slow, methodical process of gathering what was available. There was no chase, no climactic struggle between predator and prey in the modern sense. An organism's success depended on its ability to find and process the smallest morsels of food. Without jaws, there was no way to grasp, hold, or break down larger, more complex food sources. The immense energy locked away in the bodies of other animals was largely inaccessible. This fundamental constraint placed a ceiling on size, on speed, and on intelligence. A more active, energetic lifestyle required a more efficient way to fuel the body. The evolutionary stage was set, but the main actors were waiting for a revolutionary new tool. A change was coming. Deep within the genetic code of these simple, jawless vertebrates, a blueprint was being unintentionally drafted for a weapon that would reshape the planet. The gentle, slurping silence of the Cambrian seas was about to be broken. The oceans following the Cambrian were dominated by a new class of vertebrates, the agnathans, or jawless fish. Encased in heavy, bony armor, these ostracoderms were the tanks of their time. They continued the ancient tradition of bottom feeding, using their simple, jawless mouths to vacuum up detritus from the seafloor. For millions of years, they were an evolutionary success story, their bony shields protecting them from the few predators that existed. But their success masked a critical vulnerability. Their feeding strategy was inefficient, and their armor made them slow and cumbersome. They were locked into a passive existence. Meanwhile, a monumental transformation was taking place. The solution to their limitations was not a new kind of armor or a better way to filter mud, but a repurposing of an existing structure. Early fish, like all fish today, breathed using gills supported by a series of bony or cartilaginous struts called gill arches. In one group of fish, a mutation occurred. The first and foremost of these gill arches, instead of supporting a gill, began to fold forward and enlarge. It was a simple change, but its consequences were earth-shattering. This flexible, hinged structure became the first jaw. It was a hinge of fate. Suddenly, a fish could do something no vertebrate had ever done before. It could open and close its mouth with force. It could grab. This single innovation separated the vertebrates into two great dynasties, the jawless agnathans and the new, formidable gnathostomes, the jawed vertebrates. The first jawed fish were small, but they possessed an advantage that was as significant as the invention of flight. They were no longer just passive grazers. They were active hunters. They could grasp onto prey, holding it fast. They could manipulate objects, explore their environment in a new tactile way, and defend themselves with more than just passive armor. This was the dawn of a new biological arms race. The appearance of the jaw rendered the slow, heavily armored jawless fish obsolete. A predator that could bite could find the weak points in their armor. The rules of survival had been rewritten overnight. The oceans became a far more dynamic and dangerous place. The power to bite was the power to dominate. This new anatomical feature would become the foundation for nearly all future vertebrate evolution, including our own. But a jaw, as revolutionary as it was only half of the equation. It was a powerful clamp, but it lacked a cutting edge. The next evolutionary step would be to arm this new weapon, to turn it from a simple grasping tool into a lethal instrument of unparalleled efficiency. The Devonian Period. Geologists call it the Age of Fishes, and for good reason. The oceans were now a battleground, dominated by the descendants of the first jawed pioneers. The placoderms, or plate-skinned fish, had taken the innovation of the jaw and combined it with the heavy armor of their ancestors, creating a class of formidable predators. They were the undisputed rulers of the Devonian seas, and among them, one stood supreme, a creature of staggering size and power, Deadliest. This was not just a fish, it was a living fortress, an apex predator reaching lengths of up to 30 feet. Its head and torso were shielded by thick plates of solid bone, making it nearly impervious to attack. But its most terrifying feature was its mouth. Deadliest had no teeth in the way we understand them. Instead, its jawbones themselves were honed into massive, razor-sharp, self-sharpening blades of bone. When it closed its mouth, these bony shears came together with incredible force, capable of snapping other armored fish in half. This was the ultimate armor-breaking technology of its time. The bite of Deadliest was one of the most powerful in the history of life on Earth. Biomechanical studies suggest it could slam its jaws shut in a fraction of a second, creating a powerful suction force that pulled prey into its mouth before the final, decisive snap. Nothing with a shell or bony plate was safe. Trilobites, ammonites, and even smaller sharks were on its menu. The placoderms represented a pinnacle of early jaw evolution. They had perfected the art of the crushing, shearing bite. Their reign lasted for nearly 50 million years, a testament to their successful design. Yet, for all its power, the Deadliest's weapon had a fundamental flaw. Its bony blades were part of its skeleton. If they broke, they could not be replaced. It was a powerful but brittle system. Evolution, however, never stops experimenting. In another, more unassuming lineage of fish, the early sharks and bony fish, a different solution was emerging. They were developing something new, true teeth. These were separate, distinct structures rooted in the skin of the mouth that could be lost and replaced throughout the animal's life. They were more versatile, more resilient, and ultimately, a superior design. As the Devonian came to a close, the mighty placoderms, including the fearsome Deadliest, vanished in a mass extinction event. Their world ended, but the future belonged to those with the new dental innovation, the ones whose bite was not just powerful, but renewable. But for over 100 million years, the story of the jaw and teeth had been an exclusively aquatic one. But the land, a vast, unoccupied continent of opportunity, beckoned. It was a world of strange, giant insects and lush, primitive forests. For the boldest of the bony, lobe-finned fishes, this new frontier was irresistible. The transition was one of the most dramatic chapters in evolution. Creatures like Tiktaalik, a fishapod with a flattened skull, mobile neck, and sturdy, limb-like fins, bridged the gap. It could prop itself up in the shallows and look around, a simple act that was impossible for its fishy ancestors. Its jaws were still built for the water, but its body was preparing for the land. Following in its wake were the first true tetrapods, four-limbed animals like Acanthostega and Ichthyostega. As they hauled themselves out of the water, they entered a world governed by new rules. The most immediate challenge was gravity, but a close second was the simple act of eating. In the water, fish can use suction to help pull food into their mouths. In the air, that technique is useless. The first land animals had to re-engineer their jaws and skulls to cope. They developed stronger jaw muscles to grab and hold on to prey without the assistance of water. Their skulls became more robust. Crucially, they developed more pronounced, sharper teeth. On land, prey like giant dragonflies and millipedes could struggle, squirm, and escape. The simple, conical teeth of their fish ancestors were good for piercing, but on land, a firmer grip was needed. The teeth of early amphibians became a cage, a picket fence of sharp points designed to ensnare and immobilize their food before swallowing it whole. Their necks also became more mobile, allowing them to strike at prey with greater accuracy. This was the first bite on land, a clumsy but revolutionary act. It opened up the vast resources of the terrestrial ecosystem. These amphibious pioneers were successful, but they remained tethered to the water, needing to return to lay their eggs and keep their skin moist. They had conquered the shore, but not the continent. To do that, a new kind of animal would need to evolve, one that could break its ties with the water completely. This new group would take the terrestrial bite and refine it into a tool of unprecedented power and versatility, setting the stage for a new dynasty to rule the earth. The world was changing. The great steamy swamps of the Carboniferous period were giving way to the drier, more seasonal landscapes of the Permian. For the amphibians, tied to the water, this was a challenge. But for a new group of animals, it was an opportunity. These were the first reptiles. With their scaly, water-retentive skin and shelled eggs, they could leave the water behind and conquer the continental interiors. And as they spread across the land, their jaws and teeth underwent a radical transformation, creating a true reptilian arsenal. The key innovation was specialization. For hundreds of millions of years, most vertebrates had homodont teeth, a mouthful of simple, conical pegs that were all roughly the same shape and size. But in the early reptiles and their close relatives, the synapsids, something new appeared: heterodonty, the division of teeth into different types with different jobs. This was a dental revolution. Consider Dimetrodon, a famous sail-backed synapside often mistaken for a dinosaur. It was one of the first land animals to have a truly specialized set of teeth. At the front of its jaw were small, incisor-like teeth for nipping. Behind them, a pair of enormous, dagger-like canines for piercing and securing struggling prey. And at the back, smaller teeth for slicing. This was not just a cage for holding food, it was a toolkit. Each tooth had a specific function, allowing for a far more efficient way of processing a meal. This dental diversification unlocked a huge range of new diets. While carnivores like Dimetrodon were perfecting the killing bite, other groups were evolving teeth for an entirely different purpose: eating plants. Herbivory is a difficult lifestyle. Plant matter is tough and abrasive. To unlock the nutrients within, it needs to be broken down. Early herbivores developed broad, grinding teeth at the back of their jaws, creating milling surfaces to shred fibrous leaves and stems. This opened up the planet's single greatest food source. With jaws that could snap, pierce, slice, and grind, the reptiles and synapsids were armed for total domination. They diversified into an incredible array of forms, from small insect eaters to massive plant eaters, and the formidable predators that hunted them. They had taken the simple hinge evolved in the ancient oceans and equipped it with a sophisticated set of precision tools. This explosion of dental technology set the stage for the next great chapter in Earth's history, an era when their descendants would grow to unimaginable sizes and rule the planet for over 150 million years. For 150 million years, a single group of animals dominated the planet. The dinosaurs were masters of scale, and nowhere was this more evident than in their jaws. Their reign represents the zenith of reptilian dental evolution, a period of unparalleled power and specialization. At the apex of this world stood Tyrannosaurus rex. Its skull was not merely a frame for its eyes and brain. It was a weapon delivery system of terrifying efficiency. The force of its bite was immense, capable of shattering the bones of its prey with a single, devastating crunch. Its teeth, often described as banana-sized, were not the simple blades of other predators. They were thick, serrated railroad spikes, designed for puncturing hide and pulverizing skeletons, a clear indication of a feeding strategy that left little to waste. But the age of dinosaurs was not defined by the carnivores alone. The herbivores developed equally impressive dental arsenals in a constant evolutionary arms race. Triceratops, a contemporary of T-Rex, possessed a remarkable innovation: the dental battery. Hundreds of teeth were arranged in tightly packed columns within its jaw. As the exposed teeth wore down from chewing tough cycads and ferns, new ones would erupt from below, providing a continuously sharp and effective grinding surface. This was a living conveyor belt of enamel. Other herbivores pursued different strategies. The colossal sauropods, like Diplodocus, had simple, peg-like teeth concentrated at the front of their jaws. They were not for chewing, but for stripping foliage from trees. The real processing happened in their vast digestive tracts, aided by swallowed stones called gastroliths. Yet perhaps the most sophisticated dental systems belonged to the hadrosaurs, the so-called duck-billed dinosaurs. Their mouths contained complex dental batteries with multiple columns of interlocking teeth, creating a vast, grinding pavement that could pulverize the toughest of plant materials. The Mesozoic world was a grand theater of consumption, where the shape of a tooth could mean the difference between thriving and perishing. The power of the predator drove the defenses of the prey, and the abundance of plant life fueled the evolution of ever more efficient biological machinery. Then, in a geological instant, it all came to an end. A cataclysm from the sky silenced the roar of the Tyrannosaurus and stilled the grinding jaws of the Triceratops. The rulers of the bite were gone, leaving a world of opportunity for the small, furtive creatures that had lived in their shadows. A new era was dawning, and it would require a new kind of tooth to conquer it. In the wake of the Great Extinction, the world slowly healed and life diversified with explosive creativity. This new era, the Cenozoic, would become the age of mammals, and it hosted its own spectacular arms race between predator and prey. Rising from the shadows were hunters of a new and formidable design, most famously embodied by the saber-toothed cats. Their iconic canines have become a symbol of prehistoric power, yet they were not instruments of brute force in the way a T-Rex's were. Smilodon, the most famous of this group, possessed a highly specialized killing apparatus. Its enormous, blade-like canines were surprisingly fragile and not suited for struggling with bone. Instead, they were used to deliver a precise, targeted bite to the soft tissues of large prey. To accommodate these weapons, its jaw evolved to open to an astonishing 120 degrees, far wider than any modern cat. This was a hunter built for a specific kind of takedown, a specialist of the highest order. The world it inhabited was filled with prey that demanded such specialization. This was the time of the megafauna, giant mammals that presented a formidable challenge to any predator. In response to the saber, evolution forged the shield. Animals like Glyptodon, a relative of the modern armadillo but the size of a small car, were encased in a solid dome-like shell of bony plates. This passive defense was a fortress of bone, nearly impervious to attack. Other creatures, like the giant ground sloths, relied on sheer size and powerful claws to deter predators. Their simple dentition reveals a diet of leaves and twigs, a different path from the high-efficiency grazers that would come later. This period was a showcase of extreme evolutionary paths. The hyper-specialized saber was a tool perfectly honed for tackling giant, thick-skinned herbivores. The massive shells and incredible bulk of the prey were an equally extreme countermeasure. It was a world of biological titans, locked in a struggle for survival written in fang and armor. But extreme specialization carries a great risk. It ties a species' fate to a specific set of circumstances, to a particular type of prey, or a stable climate. As the ice ages began to recede and the environment shifted, the giant megafauna started to disappear. The saber, once a supreme weapon, was now a liability. The hunters who depended on giant prey found their food source dwindling, and their evolutionary masterpiece of a jaw was ill-suited for smaller, faster game. A paradigm shift was coming, one that would favor not the specialist, but the adaptable generalist. While dinosaurs ruled the land and saber-toothed cats hunted megafauna, the seeds of a profound biological revolution were quietly sprouting. The future belonged to a group of animals that, at first, seemed insignificant. The small, shrew-like mammals that scurried under the feet of giants possessed a secret weapon hidden within their mouths, a new and revolutionary dental blueprint. This innovation would allow them to outlast the cataclysms and inherit the earth. Unlike the simple, peg-like teeth of most reptiles, which were broadly similar in shape, mammals evolved heterodonty, a variety of different tooth types, each with a specific job. At the front, incisors acted like chisels for nipping and cutting. Flanking them were canines, pointed teeth for piercing and gripping. And in the back, a complex series of premolars and molars formed a sophisticated food processing station for shearing, crushing, and grinding. This division of labor was a monumental leap in efficiency. But the true genius of the mammalian system was occlusion. The teeth of the upper and lower jaws were shaped to fit together perfectly, like the gears of a machine. This precise alignment allowed for true chewing, a process that mechanically breaks down food before it is swallowed. Chewing unlocks significantly more energy from food, which in turn fueled the high-octane metabolisms of warm-blooded animals. To maintain this precision, mammals made another evolutionary trade-off. They abandoned the continuous tooth replacement of reptiles for a diphyodont system, just 2 sets of teeth for life. A set of baby teeth serves the small, growing jaw, later replaced by a permanent set that is perfectly sized and aligned for the adult skull. This dental toolkit proved to be incredibly versatile. It was a platform upon which evolution could build countless variations. Rodents evolved ever-growing incisors for gnawing through the toughest materials. Carnivores refined their back teeth into specialized shearing blades called carnassials. Herbivores transformed their molars into durable grinding mills. This fundamental combination of specialized tooth types and a precise bite gave mammals the adaptability to conquer every conceivable habitat and dietary niche, from the deepest oceans to the highest mountains. The mammalian mouth was not just for eating, it was a gateway to a new world of energy, activity, and diversity, setting the stage for every mammal that has ever lived, including ourselves. As the global climate changed, vast forests gave way to endless plains of grass. This new ecosystem represented one of the largest and most challenging food sources on the planet. Grass is tough, fibrous, and filled with abrasive silica particles that can wear down teeth with astonishing speed. To thrive here, a new kind of dental system was required, an evolutionary marvel of durability and efficiency, the grinding engine. The pioneers of this new world were the grazing herbivores, the ancestors of modern horses, antelope, and cattle. Their survival depended entirely on their ability to process immense quantities of this difficult vegetation. The solution was a radical redesign of the molar. They evolved what is known as hypsodonty, or high-crowned teeth. Unlike our own low-crowned teeth, a hypsodont molar is extraordinarily tall, like a skyscraper of dental tissue. Much of its height remains hidden below the gum line, held in reserve. As the exposed surface is relentlessly worn away by chewing abrasive grasses, the tooth slowly erupts from the jaw, ensuring a functional grinding surface throughout the animal's long life. But the genius of this design lies in its complex structure. These molars are not made of a single material. They are intricate, folded layers of 3 different substances: incredibly hard enamel, softer dentin, and bone-like cementum. As the tooth wears, these materials erode at different rates, creating a permanently rough and uneven surface. This transforms the molar into a highly effective rasp or file, perfectly suited for shredding tough plant fibers and unlocking the nutrients within. This dental evolution drove dramatic changes in the skull. Jaws became deeper and more robust to house these massive dental batteries. The muscles powering the jaw, particularly the masseter, became enormous, enabling the powerful side-to-side motion essential for grinding. The entire face of these animals elongated, creating a longer tooth row for more efficient processing. This powerful grinding engine was a key innovation that allowed herbivores to conquer the world's grasslands. They became incredibly successful, forming vast herds that transformed the landscape itself. Their abundance, in turn, fueled the evolution of new predators, like the pack-hunting wolves and pursuit cats, specifically adapted to hunt these swift, plains-dwelling animals. The humble blade of grass had forced the creation of one of nature's most sophisticated biological machines. Deep within the shrinking forests of ancient Africa, a different evolutionary story was unfolding. Here, in the dappled light of the canopy, our primate ancestors thrived on a varied diet of fruits, tender leaves, and insects. Their teeth were not the specialized tools of a grazer or a hypercarnivore. They were the versatile implements of a generalist. Their molars had low, rounded cusps, perfect for crushing soft foods. Their canines were relatively modest, and their incisors were simple tools for plucking and peeling. This was the ancestral toolkit that would eventually give rise to our own. But the world did not stand still. Climate change forced these primates from their arboreal homes onto a new, more challenging landscape, the open savanna. This transition is etched into the fossil record of early hominins, like Australopithecus. Their teeth tell a story of dietary adaptation. We see a clear trend towards larger, flatter molars with a much thicker coating of enamel. Their jaws became heavier and more powerful. These changes suggest a diet that included tougher, more abrasive foods found on the ground, things like roots, tubers, and hard-shelled seeds. One lineage, known as Paranthropus, took this adaptation to an extreme. Nicknamed Nutcracker Man, this hominin developed a truly awesome chewing apparatus. It had enormous molars, a wide, dished face, and a massive bony crest running along the top of its skull to anchor jaw muscles of incredible size. It was a specialist, built to process the very toughest of foods. But another lineage, the one that would lead to us, took a different path. With the emergence of our own genus, Homo, something remarkable happens. The trend reverses. Teeth begin to get smaller. Jaws become more delicate. The massive chewing muscles shrink. What could explain this dramatic shift away from biological hardware? The answer was not in their mouths, but in their hands. The invention of the first stone tools marked a pivotal moment in our evolution. With a sharpened rock, our ancestors could slice meat from carcasses and pound tough plant materials, doing the most difficult processing outside of the body. The jaw was no longer the primary food processor. Technology had taken its place. This outsourcing of function had profound consequences. With the evolutionary pressure on the chewing system relaxed, jaws and faces could shrink. This, in turn, may have been a critical factor in allowing for the expansion of the brain case. The mind, and the tools it created, began to shape our anatomy. We were on a new trajectory, one where culture and innovation, not the power of our bite, would define our future and change the face of the planet forever. Our story resumes not in a laboratory, but on the sun-drenched savannas of East Africa over 3 million years ago. Here, under a vast, unforgiving sky, a new kind of primate was taking its first upright steps. This was the world of Australopithecus, the genus that includes the famous fossil Lucy. While their bipedal locomotion was a revolutionary leap, an equally profound story was unfolding inside their mouths. Their teeth and jaws represent a crucial fork in the road of our evolution, a biological blueprint that would shape the destiny of all hominins to come. When we examine the skull of an Australopithecine, we see a fascinating compromise. Their canine teeth were much smaller than those of their ape ancestors. In many primate species, large, sharp canines are used for social display, a tool for intimidation and establishing dominance. The reduction in canine size suggests a fundamental shift in social dynamics, perhaps towards greater cooperation and less internal conflict. But the real story is in the back of the mouth. Their molars were enormous, with thick, durable enamel. These were powerful grinding platforms, biological millstones designed for processing tough, fibrous plant matter, roots, tubers, and seeds. This dental toolkit was perfectly suited for a creature making a living in a challenging seasonal environment. It was a versatile, jack-of-all-trades arrangement, allowing them to fall back on low-quality, difficult-to-eat foods when more desirable options were scarce. This dental strategy was taken to its extreme by a related group, the robust Australopithecines of the genus Paranthropus. With their massive dish-shaped faces, prominent sagittal crests anchoring huge chewing muscles, and gigantic molars, they were the ultimate chewing machines. They represented an evolutionary path that doubled down on powerful mastication. Our direct ancestors, however, took a different route. The Australopithecine blueprint was less specialized. It retained a degree of flexibility that the hyper-specialized Paranthropus lacked. Their jaws were powerful, but not excessively so. Their teeth were large, but not to the extreme. This anatomical compromise, this lack of overspecialization, proved to be their greatest strength. It kept their evolutionary options open. They weren't locked into a single dietary niche. This adaptable dental plan, capable of handling a varied diet, was the foundation upon which the entire human lineage would be built. It was a successful design, but one that was about to be rendered partially obsolete by a spark of ingenuity that would change our relationship with food and our own bodies forever. The sound that heralded the next great leap in our evolution was not a roar, but a sharp, deliberate crack, the sound of stone striking stone. In the hands of a new hominin, Homo habilis, or the handy man, the first crude stone tools emerged. These implements, known as the Oldowan toolkit, were deceptively simple choppers and flakes, yet they were revolutionary. They were, in essence, the first external teeth. With a sharp stone flake, our ancestors could slice through tough animal hides and cut meat from bone, tasks their own generalized teeth were not well equipped for. With a heavy chopper, they could smash open long bones to access the calorie-rich marrow inside, a food source unavailable to almost any other creature. This technological breakthrough began a process of pre-mastication. Food could be processed before it ever entered the mouth, outsourcing the heavy work of chewing to technology. This unlocked a new world of high-energy, nutrient-dense foods, fundamentally altering the energetic equation of survival. But an even greater revolution was on the horizon, glowing in the darkness. The harnessing of fire, likely achieved by a later species, Homo erectus, was the single most important dietary innovation in human history. Cooking does more than just make food taste better. It transforms it. Heat breaks down tough collagen in meat and softens the resilient cellulose in plants, making them vastly easier to chew and digest. It neutralizes toxins and eliminates pathogens, making a wider range of foods safe to eat. The biological impact was immense. With tools to cut and fire to soften, the intense selective pressure from massive jaws and enormous grinding teeth began to relent. For millions of years, a powerful chewing apparatus was a non-negotiable prerequisite for survival. Now, it was becoming less critical. We see the anatomical consequences etched into the fossil record. The face of Homo erectus is noticeably flatter and less projecting than its predecessors. The jaws are smaller, the teeth more delicate. Energy once dedicated to building and maintaining a powerful masticatory system was now being liberated. This wasn't a sign of weakness. It was a mark of profound success. Our ancestors were becoming masters of their environment, using their growing intelligence to bypass their biological limitations. As the jaw receded and the face flattened, the architecture of the skull began to change, creating new space. A new frontier was opening up, not on the savanna, but within the cranium itself. The energy saved from chewing was about to be reinvested into growing the most complex and powerful structure the world has ever known. We have arrived at ourselves, Homo sapiens. Look in the mirror, and you see the culmination of this long evolutionary journey. Our faces are remarkably flat, our chins prominent, and our jaws are delicate and small compared to any of our ancestors. Our teeth, too, have shrunk in size. We are the ultimate gracile hominin, a species that has traded brute chewing force for cultural and technological prowess. Our diet, further refined by millennia of agriculture, cooking, and food processing, has almost entirely removed the intense physical demands that shaped our forebears. This transition has been a spectacular success, but it has created a curious and often painful paradox that resides at the very back of our mouths. This is the problem of the third molars, more commonly known as wisdom teeth. For our ancestors, wisdom teeth were not a problem. They were a necessity. Their diet was far tougher and more abrasive. Grit and tough fibers in their food caused significant wear on their molars throughout their lives. As the teeth wore down, they would slowly drift forward in the jaw, a process called mesial drift. This natural movement conveniently created just enough space at the back of the dental arch for the third molars to erupt properly in late adolescence, replacing the worn-out chewing surfaces. For us, the situation is entirely different. Our modern, soft, processed diet causes very little tooth wear. Without that abrasive stimulus, our teeth no longer drift forward to the same degree. Compounding the issue, our jaws are significantly smaller than those of our ancestors. The result is an evolutionary mismatch. The genetic signal to produce wisdom teeth still exists, but the anatomical space for them to emerge has vanished. They become impacted, growing in sideways, causing discomfort, infection, and crowding the other teeth. They are a relic of a different time, an echo of a tougher diet and a more robust facial structure. Our teeth are a living record of this dietary shift. Dental anthropologists can study the microscopic wear patterns on ancient teeth to reconstruct the diets of past populations. They can analyze tartar, or dental calculus, for traces of plant matter and other food particles, revealing what was on the menu thousands of years ago. Our modern dental dilemmas are a direct consequence of our own success. We have engineered a world so soft that we have outpaced our own biology, leaving behind a ghost in our jaw that speaks volumes about the wisdom of our ancestors. The human brain is an anomaly. Weighing a mere 3 pounds, it is an organ of immense power and staggering metabolic cost. It accounts for only 2% of our body weight, yet it consumes over 20% of our energy when we are at rest. In the great biological marketplace of evolution, how could our ancestors possibly afford such a luxurious, energy-hungry organ? The answer, many scientists believe, lies not in the head, but in the gut. The expensive tissue hypothesis provides a compelling explanation. It proposes that in any animal's body, there is a finite energy budget. For one metabolically expensive organ system to grow, another must shrink to compensate. The two most costly systems in primates are the brain and the digestive tract. A diet of raw, fibrous plants requires a very large and long gut to slowly ferment and extract the necessary nutrients. This is what we see in many of our primate relatives. Our ancestors, however, embarked on a different path. The moment they began using tools to process food and fire to cook it, they fundamentally changed this equation. Cooked food is pre-digested. The heat breaks down complex carbohydrates and proteins, making nutrients far more accessible. A diet that included energy-dense cooked meat and tubers no longer required a vast and costly digestive system. As our ancestors' diet improved in quality, their guts could afford to shrink. The energy saved from no longer needing to fuel a massive digestive tract was freed up. This surplus metabolic energy was then available for reallocation to the other expensive organ, the brain. This initiated one of the most powerful positive feedback loops in the history of life. A slightly bigger brain allowed for the creation of better tools and more effective hunting strategies. Better tools and techniques led to a higher quality diet with even more calories and nutrients. This superior diet, in turn, fueled the further expansion of the brain. From the time of Homo habilis to Homo erectus and onward to Homo sapiens, we see a clear trend in the fossil record. As faces and teeth got smaller, brain cases got larger. This explosive growth in cognitive hardware reshaped our planet. It gave rise to complex language, abstract thought, long-term planning, and intricate social cultures. We literally cooked our way to a higher consciousness. The feast that fueled our minds was not just about what we ate, but how we prepared it. By transforming our food with our intellect, we transformed ourselves from just another clever primate into the architects of the modern world. From the frozen ice sheets of the Arctic to the dense jungles of the Amazon and the sprawling concrete canyons of our modern cities, a single species has conquered every major ecosystem on Earth. No other large animal has achieved such a global distribution. What is the secret to this unprecedented success? The answer is etched into our very being, starting with the versatile dental toolkit we inherited from our earliest ancestors. Humans are the planet's supreme dietary generalists. Unlike specialists, which are exquisitely adapted to a narrow range of foods, we are masters of flexibility. Consider the giant panda, which must consume vast quantities of bamboo, or the koala, restricted to eucalyptus leaves. Their specialization is a strength in a stable environment, but a critical vulnerability when that environment changes. Our omnivorous nature, in contrast, is our greatest advantage. Our teeth reflect this remarkable adaptability. We have incisors at the front for cutting and biting, like those of a fruit eater. We have canines, reduced but still useful for tearing, and we have premolars and molars at the back for crushing and grinding. This dental arrangement is not the best for any single task, but it is good enough for almost all of them. It is a multi-tool, capable of handling fruits, nuts, seeds, roots, leaves, insects, and meat. When our ancestors migrated out of Africa, this flexibility was their passport to the world. As they encountered new climates and new ecosystems, they were not restricted to a specific menu. They could adapt. If large game was scarce, they could focus on coastal resources. If a drought withered their preferred plants, they could find others. This ability to switch food sources provided a resilience that few other species could match. Our intelligence, of course, was the great amplifier of this advantage. We didn't just find food, we invented new ways to acquire and process it, from fishing nets and spear throwers to agriculture and aquaculture. This dietary breadth has been a primary engine of human history. The search for new tastes and resources fueled exploration, built global trade routes, and shaped entire cultures around the cultivation and preparation of food. We are the species that can make a meal out of nearly anything, anywhere. This has allowed us to thrive in the face of ice ages, droughts, and countless other environmental challenges. Our teeth and jaws tell a story that is more profound than mere anatomy. They tell the story of our indomitable adaptability. It is the omnivore's advantage that laid the foundation for our journey to becoming a global species. But in a modern world of overwhelming choice and industrial food production, this same flexibility presents us with an entirely new set of challenges, a true omnivore's dilemma. For millennia, the human jaw was a powerful engine of survival, designed to crush, grind, and tear through the tough, fibrous diets of our ancestors. Our teeth were the robust tools of this engine, worn by grit, but largely untroubled by decay. Then, in a mere flicker of evolutionary time, everything changed. A single, crystalline substance, once a rare luxury for kings and emperors, became a staple on every table. This was the dawn of the age of sugar, and it would come at a staggering cost to our ancient dental hardware. The story begins not in the mouth, but in the cane fields and refineries that fueled the Industrial Revolution. As global trade routes expanded, sugar transformed from a precious spice into a cheap, abundant source of calories. It fueled the long working hours of factory laborers and sweetened the lives of a growing middle class. By the 19th century, humanity was consuming it in quantities previously unimaginable. Our biology was utterly unprepared. The bacteria in our mouths, particularly strains like Streptococcus mutans, discovered a paradise. Fed by a constant supply of simple carbohydrates, these microorganisms flourished, fermenting sugar into corrosive acids. This acid bath relentlessly attacked our tooth enamel, the hardest substance in the human body, dissolving its mineral structure in a process called demineralization. The result was dental caries, or cavities, on an epidemic scale. Skeletons from before this era show remarkably healthy teeth, but with the rise of sugar, toothache became a common torment, and tooth loss a grim inevitability for millions. The gentle wear of our ancestors was replaced by the aggressive, penetrating decay that burrowed deep into the tooth, leading to discomfort and serious infections. This oral health crisis was a direct consequence of a profound dietary shift. Our teeth, forged over eons to handle the mechanical stresses of a coarse diet, were now facing a chemical assault for which they had no defense. The very food that provided cheap energy was systematically dismantling the tools we used to eat it. The problem became so widespread that it demanded a new kind of solution. It was no longer enough to simply pull an aching tooth. A new field of medicine would need to rise from this epidemic of decay, one dedicated not just to extraction, but to the intricate science of restoration and preservation. A battle for the mouth had begun. The widespread dental decay of the industrial age created a crisis that could no longer be ignored. The era of the marketplace tooth puller, often a barber or blacksmith with a strong pair of pliers, was coming to an end. Out of this necessity, a new medical discipline was born: modern dentistry. It was a revolution that transformed a dreaded ordeal into a precise science. The transformation was spearheaded by pioneers like the 18th-century French physician Pierre Fauchard, often called the father of modern dentistry. He introduced the idea that teeth should be cleaned, preserved, and even straightened. He developed instruments, described techniques for filling cavities, and proposed that acids from sugar were the cause of decay. His work laid the foundation for dentistry as a true profession. The 19th and 20th centuries brought a cascade of technological breakthroughs that would be unrecognizable to Fauchard. The invention of the dental drill, while initially intimidating, allowed for the precise removal of decayed tissue. The discovery of anesthesia, from nitrous oxide to local anesthetics, fundamentally changed the patient experience, turning terror into manageable discomfort. Wilhelm Röntgen's X-rays provided an unprecedented ability to see inside the tooth and jaw, diagnosing problems invisible to the naked eye. With these new tools came a revolution in materials science. Dentists were no longer limited to plugging holes with lead or gold. They developed sophisticated amalgam alloys, and later, tooth-colored composite resins and ceramics that could restore not just the function of a tooth, but its natural appearance. The focus began to shift from simple repair to complex restoration and, ultimately, to aesthetics. This pivot was crystallized in the field of orthodontics, systemized by figures like Edward Angle in the early 1900s. He classified different types of malocclusion, or improper bites, and developed appliances to move teeth into their ideal positions. Suddenly, the alignment of the jaw was something that could be engineered. In the 20th century, amplified by the rise of Hollywood and mass media, the perfect smile became a cultural ideal, a symbol of health, beauty, and social success. Dentistry was no longer just about avoiding pain. It was about achieving a specific aesthetic standard. We had mastered the art of building a beautiful, functional bite. But in focusing so intently on the mechanics of chewing and appearance, we were perhaps overlooking the other, equally profound purpose for which our mouths had been shaped. We have explored the mouth as a machine for eating and a canvas for beauty. But its most transformative role in the human story may have nothing to do with food. The complex architecture of our jaws, teeth, lips, and tongue gave us something unique among all species on Earth: the power of speech. This was not a minor adjustment. It was a radical reinvention of our anatomy. To understand how radical, we must compare ourselves to our closest primate relatives. A chimpanzee's vocal tract is built for simple vocalizations. Its larynx, or voice box, sits high in the throat, allowing it to breathe and swallow at the same time, a useful trick for avoiding choking. But this high position severely limits the range of sounds it can produce. In early humans, a critical evolutionary change occurred. The larynx descended, creating a large resonant chamber above the vocal cords, known as the pharynx. This anatomical shift came with a significant trade-off. It made us uniquely susceptible to choking on our food, a risk no other primate faces. Yet, the evolutionary advantage must have been immense. This new vocal arrangement, combined with a short, rounded tongue and the fine motor control of our lips and jaw, turned our mouths into an unparalleled instrument. The teeth, once solely for processing food, were repurposed as articulators. By placing the tongue against the back of the upper incisors, we can make a th sound. By pressing our lips together, we form a B or P. This intricate ballet of muscle and bone allows us to produce the vast array of consonants and vowels that are the building blocks of all human languages. This ability to communicate complex, abstract ideas, to plan a hunt, to teach a child how to make a tool, to share stories, was the catalyst for culture. Language allowed knowledge to accumulate from one generation to the next, building the foundation for complex societies, technologies, and civilizations. Our jaw was no longer just a tool for our own survival. It became a tool for the survival and advancement of our entire species. The mouth had given us a voice, and with that voice, we began to shape the world. But this remarkable instrument also keeps a record, a silent story of our lives written in the very substance of our teeth. Our bodies are ephemeral, but within our mouths lies a substance that can defy time. Tooth enamel, harder than any bone, is a biological archive. It is a time capsule that fossilizes with remarkable fidelity, preserving an intimate record of an individual's life long after they are gone. For paleoanthropologists, a single fossilized tooth can be a Rosetta Stone, unlocking secrets of the deep past. The clues are etched into its very structure. Under a powerful microscope, the surface of a tooth reveals a landscape of microscopic pits and scratches. This field, known as dental microwear analysis, acts as a dietary diary. Long, parallel scratches suggest a diet of tough, fibrous leaves that had to be sheared. Small, complex pits point to a diet of hard, brittle objects like nuts and seeds. This allows scientists to reconstruct the menu of our ancient ancestors, like the Neanderthals, and understand how they adapted to changing climates and food sources. The tooth also tells us about an individual's life journey. As teeth develop during childhood, they form in layers, much like the rings of a tree. If a child experiences a period of severe stress, such as malnutrition or serious illness, the formation of enamel can be disrupted, leaving behind permanent horizontal grooves known as enamel hypoplasia. By examining these lines, researchers can pinpoint periods of hardship in an individual's early life. But perhaps the most remarkable story is told by the chemistry of the enamel itself. As we eat and drink, trace elements from our local environment become incorporated into our developing teeth. By analyzing the isotopes of elements like strontium and oxygen locked within the enamel, scientists can determine the geological region where a person spent their childhood. This technique has become a powerful tool for tracing ancient migration, mapping the vast reach of the Roman Empire through its soldiers and citizens, and even identifying the origins of individuals buried in unmarked graves thousands of years later. From a single tooth, we can learn what our ancestors ate, the challenges they faced as children, and the lands they called home. It is a deeply personal history, a biography written in the most durable material our bodies will ever produce. As we read the stories in their teeth, we are forced to ask, what story is being written in ours? Our journey has taken us from the first predatory jaws of ancient fish to the complex, articulate mouths of modern humans. We have seen how our diet shaped our teeth, and how our teeth, in turn, shaped our destiny. But evolution is not a story with an ending. It is a continuous process, and we are living through its next chapter. Today, we face what scientists call an evolutionary mismatch. For millions of years, our jaws were shaped by the powerful forces required to chew tough, unprocessed foods. Our modern diet, however, is overwhelmingly soft. This lack of mechanical stimulation means our jaws are not developing to their full genetic potential. They are shrinking. The most obvious evidence of this is the problem of wisdom teeth. These third molars, essential for our ancestors who often lost other teeth, now frequently have no room to erupt properly in our crowded modern jaws. They become impacted, a clear sign that our anatomy is changing faster than our genetic blueprint. This shrinking of the jaw is also a leading cause of malocclusion, the crooked, crowded teeth that make orthodontics a near-routine part of modern adolescence. But as our biology struggles to keep up with our culture, our technology is racing ahead. The future of dentistry may look less like drilling and filling and more like something from science fiction. Researchers are actively working with stem cells and growth factors, exploring the possibility of coaxing the body to regrow entire teeth, just as some reptiles do today. Imagine a future where a lost tooth is simply replaced by a new one, grown in its place. Enamel, once thought impossible to regenerate, is now the subject of promising research into biomimetic materials that could help it repair itself. Smart technology is also entering the oral cavity, with sensors that could one day be embedded in a crown or implant to monitor oral chemistry, detecting the earliest signs of decay and transmitting the data to your dentist. We are on the cusp of an era of truly personalized dentistry, where our genetic predispositions to oral diseases can be identified at birth, allowing for a lifetime of targeted, preventative care. What is the ultimate trajectory? Will our descendants, sustained by nutrient pastes and liquid meals, evolve to have fewer teeth, or perhaps none at all? Or will our growing understanding of biology and technology allow us to guide our own evolution, maintaining our dental heritage in a world that no longer demands it? The story of the human mouth is the story of humanity, a relentless drive to adapt and innovate. The next chapter is being written with every meal we eat, every word we speak, and every scientific discovery we make. The future of a mouthful is the future of us all.